This video is about partial differentiation. If z is a function of two independent variables x and y, then we can differentiate z with respect to x or with respect to y. Or z can be differentiated with respect to both x and y. Now, if z is differentiated with respect to only one variable, so let's say, for example, we differentiate z with respect to x only, then we have to take y as a constant. Then that differentiation process is called partial differentiation. Now, in partial differentiation, instead of using small d in our notation, we'll be using the small letter for delta. So, if we want to differentiate z with respect to x only, then we'll have the partial derivative of z with respect to x, denoted by this. Or it can be denoted by z sub x, meaning z is differentiated only with respect to x. Okay, so this is equal to f prime of xy. Okay, take note that in this differentiation, y is taken as a constant. Alright, so this can also be written as f sub x. So it means to say that we differentiated f with respect to x only. Now, if we want to differentiate z with respect to y, then our notation would be partial derivative of z with respect to y. It would be in this form. Or you can also write this as z sub y, meaning you differentiated the function z with respect to y. So f prime of xy with respect to y. So I'll write y here. So f sub y, and then use x here. Just to say that we have differentiated the function f with respect to x or y only. So in this case, x is taken as a constant. So in some books, you'll not see this apostrophe anymore. So you can just write f sub x of xy and f sub y of xy. Alright, so we can take this notation. These notations. Okay, so they all mean the same thing. So the notation will just depend on how we have written the function. Okay. So let's say, for example, the function is written as z equals, right, xy squared plus 2x squared y cubed. Now, if we want to differentiate z with respect to x, then we can have the notation partial derivative of z with respect to x. So in this case, you can also make use of the notation z sub x. Okay, they mean the same thing. So z sub x, or the partial derivative of z with respect to x, we read this in the same way, is equal to. So in this case, we take y as a constant because we are differentiating with respect to x. Okay, so if we have a constant in the first term, this is the first term, xy squared. So y squared is just a constant. Let's just copy that. So the derivative of x with respect to x is just 1. So that's it. For the second term, 2x squared y cubed. 2 is a constant, no doubt. And then y cubed is also taken as a constant, taking the partial derivative of z with respect to x. And then the derivative of x squared with respect to x is 2x. So the partial derivative of z with respect to x is equal to y squared plus 4xy cubed. Alright. Now let us take a look at the partial derivative of z with respect to y. So, or you can denote this by z sub y. Okay. So in this differentiation process, we have to take x as a constant. So in the first term, xy squared, take x as a constant. So just copy the constant and take the derivative of y squared with respect to y. And we'll get 2y. Plus, in the second term, we have 2 as a constant and also x squared. Alright? And we take the derivative of y cubed with respect to y. Using power rule, we get 3y squared. So the partial derivative of z with respect to y is equal to 2xy plus 6x squared y squared. Okay. Now, because these two partial derivatives are still functions of the same two independent variables x and y, we can therefore differentiate both of them with respect to x or with respect to y. So each of these first derivatives or first partial derivatives will have two derivatives again, and those are called the second partial derivatives of z with respect to x or y. Alright, so we still have here the first partial derivative of z with respect to x and the first partial derivative of z with respect to y. So we know that these two are both functions of x and y. So if we want to differentiate this again with respect to x, then we'll have the second partial derivative of z with respect to x. And that is denoted by second partial derivative of z with respect to x. Alright, and we can denote this using the other notation, using f. So x of xy. It means to say that in the first partial derivative, we have differentiated f with respect to x. In the second partial derivative, we have differentiated f with respect to x again. Now, if the first partial derivative of z with respect to x is then differentiated with respect to y, then the second partial derivative of z with respect to y would be denoted by this, with respect to y. So it means to say that the first partial derivative of z is with respect to x, and the second partial derivative of z is with respect to y. Or using the other notation, if x, it's f sub xy of xy. So it means to say that we differentiated first with respect to x and then with respect to y after. Just to make things clear, so this is when the first partial derivative was done with respect to x and the second partial derivative was done also with respect to x. Now this, the first partial derivative was done with respect to x and the second partial derivative was done with respect to y. Take note of the different notations. Now let's go to the first partial derivative of z with respect to y. So if we want to differentiate this first partial derivative with respect to y, now with respect to x, then the second partial derivative of z with respect to x would be denoted by this. So second partial with respect to x, first partial with respect to y. Or in another notation, that is f sub y x, xy. Okay? Or if we want to differentiate differentiate z again with respect to y, then we'll have the second partial derivative of z with respect to y in this form. So that's f sub y y xy. Okay, take note that in this equation, the first partial derivative was done with respect to x and the second partial derivative, the first partial derivative was done with respect to y and the second partial derivative was done with respect to x. Let me just write that down. Alright, so first partial derivative with respect to y, second partial derivative with respect to x. Now for the other one, first partial derivative was done with respect to y and the second partial derivative was done with respect to y also. Now in our previous example, we have here the first partial derivative of z with respect to x. We can also take the second partial derivative of z with respect to x. So first partial derivative was done with respect to x, second partial derivative will be done with respect to x also. So if you are differentiating partially with respect to x, don't forget to take y as a constant. So in this function, we differentiate now partially with respect to x again, so we'll take y as a constant and all the powers of y also. So in the first term, y squared, that is just a constant. So the derivative of that constant is 0. Okay. Plus, in the second term, 4xy cubed, we take y cubed as a constant, and also 4 is clearly a constant. And then the derivative of x with respect to x is, of course, 1. So the second partial derivative of z with respect to x, first partial with respect to x is equal to 4y cubed. Right? Now, what is the second partial derivative of z with respect to y? the first partial with respect to x. So we'll still be differentiating this function with respect to y this time. So we'll take x as a constant. So we'll have the first derivative, the derivative of y squared with respect to y is 2y. Plus, for the second term, we'll take x as a constant. So there's a constant equal to 4x in the second term, while the derivative of y cubed with respect to y is 3y squared. So the second partial derivative of z with respect to y, first partial with respect to x, is equal to 2y plus 12x y squared. Okay. So, forgot to box this. Now, let's look at the function for the first partial derivative of z with respect to y. So, we can take the second partial derivative of z with respect to x, while the first partial was done with respect to y. So, we are differentiating now with respect to x. So, we'll take all y's and the power of y's constants. Okay, so in the first term 2xy, we'll take 2y as a constant, and the derivative of x with respect to itself is 1. So plus, in the second term 6x squared y squared, we'll take 6y squared as a constant, and we'll take the derivative of x squared with respect to x, and we'll get 2x. So the second partial derivative of z with respect to x, first partial with respect to y, is equal to 2y plus 12x y squared. Okay. And then, of course, we can take the second partial derivative of z with respect to y also, where the first partial was done with respect to y also. So in this case, we are differentiating partially with respect to y, so we'll take all x a constant. Okay, so in the first term 2xy, 2x is a constant, and the derivative of y with respect to itself is 1. Plus in the second term 6x squared y squared, 6x squared is a constant, the derivative of y squared with respect to y is 2y. So the second partial derivative of z with respect to y and the first partial with respect to y is equal to 2x plus 12x squared y. So these 4, 1, 2, 3, 4 are the second partial derivatives of z with respect to x and y. Okay, so if you'll notice, this is equal to this. Are they always equal? They will always be equal if the function z, this given function, is continuous.